In the heart of the lifeless Taklamakan Desert, a railway more than 2,000 kilometers long cuts through billions of tons of sand. A project that made even American engineers take notice of China's determination. It's a feat that cost President Xi Jinping's government over $3.5 billion and required more than 12,000 workers across a full decade to complete, now standing as one of the greatest symbols of modern engineering. But how did they manage to fight through fierce sandstorms and scorching heat to turn that sea of desert into the world's longest railway network? Join Mandarin Tech as we uncover the story behind this extraordinary achievement. For decades, China's northwestern region, Xinjiang and the Tarim Basin, remained a blank space on the national map, a vast, isolated land split by two massive mountain ranges and the Taklamakan Desert, which covers more than 127,000 square miles. In summer, surface temperatures can exceed 160 degrees Fahrenheit, while in winter they can drop to minus 13 degrees Fahrenheit. There's no water, no electricity, and beneath the feet lies nothing but shifting sand, no solid foundation to build upon. Yet hidden beneath that unforgiving sea of dunes lies billions of tons of untapped energy and minerals, oil, coal, and most notably, rare earth elements, the materials considered key to global technological dominance. To unlock these resources, China had no choice but to undertake what was once called an impossible mission, building a railway across the desert. So the Hotan-Rokiang Railway was built, 890-kilometer long, as part of the Taklamakan Desert Loop, a 2,685 kilometers circular railway network running along the southern edge of the desert. Completed in June 2022, it is the longest desert railway in the world. Before a single bridge or rail was built, Chinese engineers faced a question that seemed impossible. How do you choose a route across a landscape that never stops moving? They began with high-resolution satellite imagery, ground-penetrating radar, and thousands of wind measurements to determine prevailing wind directions, dune movement, and zones with relatively stable ground. Survey teams spent months living deep in the desert, drilling hundreds of boreholes, some tens of meters deep, to study the layers beneath the sand. Every route marker was placed by hand and recorded with centimeter-level precision. The line had to avoid the wind corridors where sandstorms could sweep away entire trains, yet remain close enough to access oil and coal fields along the Tarim Basin. This was the very first step in turning what was once a blank, white space on China's map into a steel curve wrapping around the desert. Before construction could even begin, hundreds of local farmers were called in to tackle a task that seemed simple, but would decide the project's fate: anchoring the sand. They bundled straw, dry twigs, and thin bamboo into long sheaves, then planted them into the ground in a checkerboard pattern. Each square measured exactly 1 square meter and was arranged diagonally at 45 degrees instead of straight lines. This layout broke the wind's direct flow, scattering its force in different directions and forcing the sand to settle within each grid. Under a blistering heat of more than 140 degrees Fahrenheit, the farmers pressed each bundle deep into the soft dunes and covered it with an extra layer of twigs to make it hold. The first few grids quickly spread across the horizon, forming thousands of organic sand fences that stretched all the way to the farthest dunes. After several months, these straw checkerboards blanketed hundreds of acres, turning the once shifting desert into a patchwork of golden brown and green. The sand stopped moving, the ground hardened, and heavy trucks could finally drive without sinking. On this newly stabilized foundation, the massive desert construction could finally begin. After the sand surface had stabilized, the next challenge was to reshape the terrain. Hundreds of bulldozers were deployed to flatten the dunes, cutting down the high ridges and redistributing the sand into lower areas. The goal was to create a smooth, balanced surface strong enough to support construction machinery without the risk of collapse. Each section was carefully scraped and leveled under strict supervision, with surveyors checking elevation and slope to ensure uniformity across miles of open desert. Conveyor systems pushed the excess sand away from the work zone, while compactors gently pressed the top layer to form a firm and workable foundation. After the bulldozers had leveled the dunes, the sand still needed to be stabilized. Engineers discovered that injecting water into the loose surface helped bind the grains together, creating a denser and more cohesive layer. Using long sprinkler arms and underground pipes, they sprayed controlled amounts of groundwater across the site, allowing moisture to penetrate several inches deep. Once the sand reached the right level of dampness, heavy rollers moved in, compacting the surface to remove air pockets and lock the particles in place. The constant rumble of steel drums echoed across the desert as each pass of the roller turned soft, shifting sand into a firm, uniform base. By the time the surface dried under the desert sun, it had hardened enough to carry the weight of cranes, mixers, and supply trucks. A solid foundation built from nothing but sand and water. After the surface had been compacted, workers began spreading a base layer of soil over the stabilized sand. Dump trucks poured out loads of reddish earth, which bulldozers then pushed and leveled across the area. This layer added weight to the sand below, strengthening the surface and keeping it from shifting under heat or vibration. Each section was evenly spread and compacted, forming a dense, stable base strong enough to support the first stages of construction in the desert. Once the ground base was fully stabilized, workers began erecting the bridge pillars. To build them, they had to drill through dozens of feet of loose sand until reaching the solid gravel or compact soil beneath. Reinforced concrete pile drivers operated day and night using steel casing pipes and bentonite slurry to keep the boreholes from collapsing. Concrete was poured from the bottom up through tremie pipes to prevent air pockets, while the steel cages were positioned with millimeter precision. Even the slightest misalignment could cause the pile to tilt or lose stability. Because daytime and nighttime temperatures differed by more than 130 degrees Fahrenheit, construction crews worked mostly at night, when the wind was calm and the sandstorms eased. Thanks to these steel and concrete piles, the railway's foundation seemed to grow roots deep into the desert. On top of those foundations, 11,000 bridge piers began to rise, row after row, forming a vast concrete forest stretching across the desert. Each pier stood between 16 and 50 feet tall. The shafts were cast using slip-form molds, reinforced with galvanized steel and salt-resistant additives to withstand the desert's corrosive climate. The short, uniform spans between piers were designed to minimize the effects of wind and extreme temperature changes. As the sun set behind the Kunlun Mountains, the endless lines of pillars stretched toward the horizon, a skeleton of steel and concrete unshaken by the desert winds. On top of those pier caps, thousands of pre-stressed concrete box girders were lifted into place using heavy crawler cranes or self-launching gantries. Each girder was over 100 feet long and weighed several hundred tons. They were transported on specialized flatbed rail cars and hoisted one by one onto the piers. Engineers then aligned the girders with laser precision, keeping tolerances within just a few millimeters. Once the spans were secured, crews poured the bridge deck slabs or installed precast concrete panels, forming a smooth surface for the tracks. Every span was spaced to allow wind to sweep freely beneath, carrying drifting sand away so it could never bury the line. More than 65% of the Hotan-Rokyang Railway, about 310 miles, runs on these elevated viaducts. From above, the railway appears like a silver ribbon cutting across an ocean of gold, a living monument to human ingenuity against one of Earth's harshest landscapes. Next, these concrete blocks being installed are called sleepers, or railroad ties. They're placed evenly along the track bed to hold the steel rails in position and distribute the weight of passing trains. Workers align each sleeper precisely, then use a lifting frame to lower the rails onto them. Once fixed and fastened, they keep the track straight and stable, preventing it from bending or shifting under heavy loads. A crucial step before the trains can safely run through the desert. After the sleepers were secured, crews began laying the steel rails on top. Each rail, stretching more than 260 feet long, was lifted into place by specialized cranes and carefully aligned along the center line. Workers adjusted every joint and gap to allow smooth expansion under heat, then tightened the fastening clips that locked the rails onto the concrete base. It took 11 months of continuous work to complete the hundreds of miles of track stretching across the desert. When the final bridge span was completed, the entire line entered the testing phase. Engineering trains ran up and down the route to measure settlement, vibration, rail temperature, and wind-induced sway. The bridges were load-tested with trains weighing thousands of tons. Results showed elevation deviations of only a few millimeters, even after hundreds of test runs. Thanks to the elevated design and natural airflow beneath the viaducts, no sand accumulated on the tracks. All operational data flowed to the control center through IoT sensors and solar-powered cameras that monitored every section in real time. After 6 months of rigorous testing, the Hotan-Rokiang Railway officially opened in June 2022, completing the 1,685-mile loop that circles the Taklamakan Desert. Along with the railway, China also built a highway that cuts directly through this vast desert. The Tarim Desert Highway, considered one of the most ambitious infrastructure projects in Western China. It was constructed to link the two oasis cities of Luntai and Minfeng, stretching for more than 300 kilometers across the desert's core. Work began in 1993, and the highway officially opened on October 4, 1995. After just over 2 years of construction under harsh conditions, shifting dunes, violent sandstorms, and searing heat that reached over 122 degrees Fahrenheit. The project cost an estimated 1.75 billion yuan, or roughly $260 million. Beneath its asphalt surface lies a multi-layer foundation of gravel, straw mats, and geotextiles designed to stop the drifting sands from bearing the road. Today, the Tarim Desert Highway not only connects isolated solar farms and scientific research outposts, but also acts as a passage for ecotourism, leading travelers through what was once among the most inhospitable landscapes on the planet. To power both the desert highway and railway, China installed a massive solar panel system across the region. This area receives more than 2,700 hours of sunlight each year, ranking among the highest in solar radiation anywhere in the world. Instead of letting the scorching sun continue to burn the sand, engineers turned it into a vast source of renewable energy. Along the Tarim Desert Highway, which stretches for more than 436 kilometers, they built 86 solar-powered pumping stations. Each station is equipped with hundreds of photovoltaic panels, generating electricity to pump groundwater from depths of over 100 meters. That water is then carried through an underground pipeline network and distributed using drip irrigation technology, allowing more than 200,000 trees along the highway to survive in a region that receives almost no rainfall. As a result, the Tarim Highway has become the world's first carbon-free desert expressway. A place where sunlight generates electricity, electricity produces water, and water sustains life. In Taklamakan, solar energy does more than power streetlights or run water pumps. It sparks hope for environmental renewal. Once known as the Sea of Death, this desert is now becoming one of the world's largest ecological laboratories, a place where sunlight, technology, and human determination come together as one. And as transportation became more accessible, tourism in the desert began to thrive. Along the edges of the Taklamakan and Gobi deserts, vast man-made forests, solar farms, and water reservoirs have been developed into parks that combine scientific research with tourism experiences. In some regions, community-based tourism is growing, blending ecotourism with the Uyghur and Mongolian cultural heritage. Travelers can join camel riding tours that cross the desert, lasting anywhere from 2 to 5 hours depending on the route, passing over rolling dunes like ocean waves and stopping at rest areas set up in the middle of the sands. Each trip costs between $40 and $120. By combining conservation, education, and real-world experience, the Taklamakan Desert today stands not only as a symbol of ecological restoration technology, but also as proof that humans can live in harmony with nature. So you have discovered the whole way the Chinese built railways in the desert. In the middle of the scorching sand, people dared to build bridges that defy nature, connecting two shores of the impossible. From steel, concrete, and desire, They have turned the desert into a symbol of will and intelligence. And if you want to continue to discover the works that are rewriting the limits of this world, click like and subscribe to Mandarin Tech, where every step of technology is told through the story of people.